this. Okay, so we are at our screen. Now, a very brief recapitulation of what we did last time. We understood what are non-deterministic automata. Basically, a non-deterministic automaton from a state on a letter may have 0, 1 or more transitions possible. Yeah. So whenever you encounter, for example, here, the transition function of this delta of P on letter 0 will take you only to the set of states 0. That is, there is only one choice. But delta of P on a 1 gives you two states 0, 1, and you have a choice of whether to go to, sorry, what am I writing? Excuse me. This gives you the set P. So you can only go to P from P on a 0, but from P on a 1 you can go to PQ, right? So there is a choice of going to either P or to Q. And the power of non-determinism is that you make an inspired guess, the best possible guess, which will take you to a state which will lead to acceptance as much as possible, right? So these are if you like, automata with inspired or lucky guesses. Some people say this kind of non-determinism is angelic non-determinism. There is an angel sitting here. Whenever you encounter a 1, it will tell you which of the two choices to make. Okay, so all this is clear to you. This is the nature of the transition function, which returns a set of states. And from that, we define the extended transition function delta hat, right? So let me and we know how to calculate this one, right? So for example, here is the calculation of delta hat starting from the state P on string 0, 1, 0. And you were even asked about how to calculate this. Let me do one more example here. Let me say I want to calculate delta hat starting from set of states PQ on a string 0, 1, 0. Same string, but I'm starting from non-deterministic from either P or Q, right? So what will I have? I will have here, I had a certain convention here. So there are these two states, P and Q, with which we begin, right? And after consuming the epsilon string, we will be in this set PQ. Now on receiving the next letter, which is 0, what will happen? P will go to P itself, right? And Q will go to R, because that is what your transition function says, that from P on a 0, you go to the state P. From Q on a 0, you go to R. So this is what you get after a 0. Okay. Then after next one, what is going to happen to this? This is what we would calculate. This would, by the way, okay, we'll see in a moment. It's not difficult. So P on a 1 will give you two states, which is P and Q. I should write on the side because, and R on a 1 cannot go anywhere. There is no transition going out of R anywhere. So this will die, right? So what you will get is from this set of states PR, on consuming a 1, you will go to the set of states PQ. This X is a dead run, so we don't count that, right? And then on another 0, P will go to P and Q will go to R, right? So as a result, we will get the answer of this delta starting from PQ on string 0, 1, 0. You wind up with the set of states PR. So this gives exactly the set of states which you will reach starting from PQ on the word 0, 1. This was, sorry, this was also a 0, right? So the calculation of delta hat is clear to you. This is what we did last time. Okay. Important thing here is that given a previous value of the set, such as this, let's call this set A, On a letter, we calculate the next step, and this step we repeat one again and again. So from A, we calculate B. And what is the rule by which we calculate B? It is this rule. Uh, let's see that here. This rule. That is delta hat of A on a letter A is equal to, you take every state of A and to calculate the delta of QA and take the union of these sets, right? So let me illustrate that here once again, or let me illustrate that here. Suppose your A is equal to the set PQ, okay, then delta hat of A on a letter, let's say 1, right, will give you what is equal to delta of A contains two sets, P and Q. So first I should apply delta to P on a 1 union delta of Q on a 1, right? And this is a very important calculation. You should remember that. Given a set and a letter, how do you calculate delta hat, of the set of states reached after consuming a single letter 1 from A? So delta of P on a 1 will give you what? It will give you PQ, and Q on a 1 will union R. So what you will get is the set of states PQR. Now you have to be absolutely clear about this one step of calculation. That is, from a set of states A on a letter 1, which is the set of states you can reach, right? And then, so from A on consuming letter 1, you will reach here. And then from this set of states B on consuming 0, you will reach this set of states T. So you iteratively apply this on letter 1 by 1, and finally you wind up with delta PQR. This calculation can also be done like this. Okay. So I hope you are clear about all this. This is last time we saw some properties of this function delta hat. So for example, to calculate what is the set of states you reach after a string xy from A, you first calculate what is the set of states that you reach from A on X. And from that set, you calculate what are the set of strings that you reach on Y. So this is just splitting up the calculation of XY into a calculation after X and then after Y, right? So decomposition. Another one, this is the very important theorem. That is, from a set of states A on an X, if you reach set B, then for every element of B, there exists some state in A such that there is a run from P to Q. This should be clear from this example. If after string 010, starting from PQ, I reach this set PR, then for every state in PR, such as let's say this R, there exists a state in this set PQ such that there is a run from so here there's a run from P to R, right? You just go down this tree this way. And so for every ending state, if you take any state in this set C, there will be a state in A from which you can have a run to that state in C. So every state has an ancestor in every state in C has an ancestor in A. Vice versa may not be true. So from this Q there is nothing going to C because the run dies off. But for everything in C there is an ancestor in P. So everything in A may not have a descendant in C, but everything in C will have an ancestor in A. So I hope this point is clear to you, right? This is a critical property. And then when we instantiate this property by taking A to be the set of start states of the NFA and taking B to be the, okay, and then calculate B, we will get this condition, which we saw yesterday, that a string is accepted by the non-deterministic automaton if or only if the set of states reach from S on string F, X has a final state in it. This intersection F equal to non-empty just says that this set has some final state in it. And so from that final state, there will be an ancestor in the set of initial states. And so there will be a run from an initial state to a final state and the word will be accepted. This is if and only if condition. So we saw all this yesterday, right? And there was a quiz question which asked you to identify this condition for NFA. Okay, we did this. So this is the alternative definition of language of a non-deterministic automaton. Language of the automaton is all words X such that N accepts X, and N accepts X if and only if delta hat of Sx has non-empty intersection with set of final states F. Okay. Now, there was another question. If you take an automaton like this, let's go back. An automaton like this. How would you implement this in using a digital circuit or a C program? If it was a DFA, what you could do is you could just remember in a variable which state you are in. This is a finite enumeration, and every time you get a letter, you will using an if then else statement. Depending on the letter, you will move to the next state. So you will assign to the current state the value of the next state. So it's very easy to simulate a deterministic finite state automaton in a program or in a circuit. In a circuit, you would remember the state by means of a bunch of flip-flops. So, if there were 4 states, you would use 2 flip-flops. Its value 0, 0, 0, 1, 1, 0, 1, 1 will represent the 4 states, and you would build a small logic which will take you on a given input letter, take you to the next state. So it's easy to implement DFA, right? So let me easy to implement DFAs, right? Because they are deterministic. There is no guessing involved in their working. So you can easily build this mechanism. What about NFA? How will we implement this? Because somewhere here we have to make this inspired guess. So if you, in your simulation, a simulator that you have built, if you are at state P and a 1 occurs, now what will you do? Will you go to Q or will you remain in P? So any thoughts on how we can implement this non-deterministic guessing automaton? Yeah. Suppose you are asked to implement this in a C program, which will recognize the same language as this automaton. What would you do? You can even answer on chat if you like, So you see, there is an issue here. I'm not saying that, I mean, you're not stupid in not coming up with an answer right away, but there could be several answers. We can store the whole string. We can process it from left to right, taking one set of choice every time a 1 occurs. And if that choice does not lead you to a final, if it leads you to final state, you will accept the word. If it not, you will backtrack and try the other choice. So you will try whole tree of choices possible on that word, and then you will exhaustively explore that tree of possibilities, and then, something like this tree that we drew here, right? Oh, okay, I have erased that tree. Yeah. Here I had drawn not this. Yeah, this tree of run. We would have to somehow simulate this whole tree and then find out if there was a final state we could reach, right? So that's a complicated program, and of course, So the crucial question that people asked was, what is the use of this non-deterministic automata? And why should we have them, since it is not so easy to implement straightforwardly in either C or in circuits? So now, is that answer to the quiz question clear, that NFA are not possible to be implemented straightforwardly? Any doubts there?
No, sir.
Okay, good. So people questioned this notion of automata with guesses when it was proposed. But then Rabin and Scott, who proposed it, said that actually, whatever we need to check whether a word is accepted by an NFA can actually be mimicked by constructing a DFA which will accept that word. So basically the idea is, given an NFA N, we can, using what is called subset construction, you will create a DFA called M, and we will have this property that the language of N will be same as language of M, where N actually accepts using the power of smart guessing, inspired guessing, whereas M does not require any such power. Of course, in order to do that, M will use many more states, it will be a more complicated automaton, but it will be able to do the same job without guessing as N. And this was the major contribution that they came up with. So this is called the subset construction. One of the great results of Rabin and Scott then, not so difficult, but conceptually this was difficult for people to understand how to handle guesses in machines, you know, and that is why this construction is famous, and we are going to learn that construction today, right? So is the intent of what they are trying to do clear? Now here we are going to have two automata. There is going to be an automaton called N and the non-deterministic automaton, and also a deterministic automaton. So this will have a set of states, you know, Qn. Because I have to distinguish the set of states of M from N, I will call the set of states of N as Q subscript N and the set of states of M as Q subscript M. So there is a little bit of notation here. Huh? Because we are dealing with two automata simultaneously, I have to use all these subscripts. Of course, both automata have the same alphabet, but the set of states of non-deterministic automaton is Qn. The set of states of deterministic automaton is Qm. Similarly, the set of start states of the non-deterministic automaton is capital Sn, and it's a set, a subset of Qn. Whereas the start state, the unique start state of M will be denoted small sm. Set of final states of N will be Fn, and that will be Qn, right? So we have to somehow construct M given N, right? And with the property that the language accepted by the two automata is the same. And that is what we are going to see today. All right. So the construction is actually given in these 4 lines. And since we have seen this delta hat function, the construction becomes very simple. We have also seen this accepting, this acceptance condition. So this is easy, but I want to do this step by step. There is a lot of symbols here. So, one of the things you learn in automata theory is to say your simple ideas out formally in precise mathematical notation, right? So before we see this formal definition, let us do this subset construction by an example, and then this will become very easy to see. So first thing is to find out what are the set of states of my deterministic constructed automaton M. That is, what is Qm, right? This line. So what is Qm? It is the power set of Qn. That is set of all subsets of Qn. Okay. So the sets of states, subsets of Qn will become the states of Qm. Let me illustrate this. Here I have two states, P and Q. The names were not given. And is this automaton clear? From P on an A you will stay in P, or you can go to Q. From P, if you get a B, there is nowhere to go and the run will die. Similarly, from Q on a B, either you can stay in Q or non-deterministically move to P, but if an A occurs, the run will die. And the start state is just P, it is, and the final state is also P. So this automaton has a single start state and a single final state. So is this automaton NFA clear to you? This is the NFA given to us. Now what Rabin and Scott said was, in the DFA, what will be the set of states? So I will draw them here, Okay, what is the alphabet? A and B, 2 letters. You can see that from the transition function. Now we are going to write the transition table of the constructed DFA. Now what they say is the set of states Qn is PQ, right? What are all possible subsets of this Qn possible? Firstly, there is the empty set phi, right? Nothing in it. Then there is the set containing only P. Then there is the set containing only Q. And then there is the set containing PQ. These are all possible subset of Qn, right? And these 4 will be the elements of the set of states of my DFA. So my Qm, if you like, will consist of, the set phi, the set P, the set Q, and the set PQ. Now you may think that, what is all this? Instead of having sets, states, we are having sets. That's not the case. This is just the name of the 4 states. I could have called them S0, S1, S2, and S3 also. It is just that for convenience, we are naming it like this. Okay. So my QM, my automaton is going to have 4 states, and I'm going to draw them here. I'm going to have a state called P. So I will draw this here. I will have a state called P. Then I will have a state called phi, empty set. Then I will have a state called Q. Yeah. And then I will have a state called PQ. So I will not draw curly brackets everywhere. I'll just write PQ, right? And curly bracket is implied. So I have this automaton with 4 states. Agreed? That is the automaton that I get. This is the first thing they said. In constructing an NFA to DFA, you first take all subsets of Qn and they become your states. So we get 4 states here. Any confusion here? No, right? One more example. Here I have an automaton with 3 states. So my Qn is equal to PQR. Now what is going to be in my DFA? What are going to be my states? I'm going to get all possible subsets of this. Since this is 3 elements, I'll have 2 raised to 3, 8 elements in my set of states, right? And that actually, if you like, is listed in this table. Okay, so I have empty set, I have just P, I've got just Q, just R, PQ, PR, QR, and PQR. So this is my set of states. So I hope the set of states of the deterministic automaton is clear to you. So that is the first line. Okay, let's not look at the second line at the moment. What is the start state? The start state of the DFA is same as the set of initial states in N. Remember, N can have a set of starting states, 1 or more, right? In fact, 0 or more. So this Sn is a subset of Qn, right? And NFA can have more than one start state. So this Sn will be one of the elements of Qm, because Qm consists of all subsets of this. So here, what is my start state of this NFA?
P.
Just set containing P, right?
Yes.
So this will become my start state, and I will mark that by putting a blue arrow in front of it. So here is my start state. This set of start state Sn, which is an individual state of DFA, becomes my start state, right? Agreed?
Yes.
Yeah. So in this case, also I have a single start state, right? P. Right? This automaton has a single start state P. Right? So the set of its start states is just the set P, right? And so this set becomes my start state. If it so happened that I allowed this automaton to start in both PQ, then this will become my start state, not this. Agreed? So I hope you are clear about the start state of the DFA that we constructed. Just copy. Yes.
Can you repeat the last Q part?
Yeah. So this is clear because for this automaton, what is my set of start states?
Only P. Bracket of P.
Yeah, just P. And so this set containing P in the DFA becomes my start state. Because what are the set of states of my deterministic automaton? All these. What I have listed. Each row is identified with one state of the DFA. Right?
Yes.
And this will become my start state. Now I give you another example, not this example. Suppose I change this automaton to have 2 start states, P and Q. So my set of start state is PQ. Then I will not put this arrow here, but I will put this start state arrow here. Remember, deterministic automaton can have exactly one start state. So I have to put one initial arrow, right?
Okay.
Yeah, simple. So I will delete this layer. Okay, so we did this. So I hope you also know how to construct the start state in the DFA, right? We have done this. Let's forget the set of final states. Now let us look at the transition function. Now what should we do? Okay, we have 2 letters A and B. So our columns will be labeled A and B, right? There will be transition on A and there's transition on B. Now the idea is that in this DFA, from a state such as curly bracket P, starting from P, on a letter A, where all can we go? Now from a set of states on a letter A, where can we go in the NFA? This we define as delta hat, right? remember we had delta hat of a set of states on a letter. This we defined, right? For an NFA. What was this defined as? Union of Q belonging to, for every state in A, you take delta of QA and take their union. We did that calculation before, if you like. I will remind you again because some of you will have forgotten. Here. Sorry, not even here. Yes, here. So given a set of states, delta hat of that set on a letter will be given by taking each of these states in A, calculating delta for it, and taking the union of the results. So here was the simple calculation, right? And that is exactly what we do in this constructing this DFA. That is, from the set of states on a letter, we will go to delta hat of that set on that letter. And that is given here, this blue arrow, right? So from a set of states A of the, and this set of states A in NFA is actually one state in DFA, right? So in the DFA, from that state called capital A, on a letter A, what will you go? You will first calculate in NFA, from that capital A on A, which set of states you can go to. That set of states will be one of the states of DFA. That is the state to which you go. So I know this is a little convoluted, but when we do the calculation, this will become very clear. Now, can somebody tell me? I'm going to write. So let's start with P, the set containing only P on a letter A. So where should we go? So we should go delta hat on this curly bracket P, which is my current state, on a letter A. Where all can I go? Can somebody give this to me? This is same as delta because there is only one state. I don't have to take any union, P on an A. And what is delta of P on an A? From P on a letter A, where all can we go? Both PQ.
P or Q.
Right. So the answer we will get here is, I will write it in red, will be P comma Q. This is the set of states that we go to. Now this PQ is the name of this state S3 in my DFA. So from this state, which is called curly bracket P, I go to a state called curly bracket PQ. Remember, this is just a state. It is not a set of states. Is this distinction clear to you? See, what is set of states in NFA becomes a single state in DFA. And this set is just the name of that state. Okay, so from this state, we could have alternately called it S1. We will go to this state called curly bracket PQ, which is also called S3. So is this clear to you how we have calculated this? If there is any doubt, this is the time to ask. Now, what is from P? Where can on a B? Where all can we go? From set of states P, if a B occurs, where can we go? Nowhere. There is no transition going up, right? So you go to empty set, fine, which is you go to this state. So first we said that from this set of states P, on occurrence of letter A, you go to PQ. So you have a transition like this on a letter A, and from P on a letter B, you will go to the empty set of states, right? So I have this kind of transitions in my automata from the state called curly bracket P. Is this clear how we constructed these two transitions?
Yes, sir.
Okay, so then somebody has to tell me and not the same person. So from Q, set of states curly bracket Q on a, where will I go?
Nowhere. 5.
5. Okay, somebody else from Q, curly bracket Q on a B, where will I go? Somebody else?
Bracket in PQ.
Sorry. P and Q, somebody said. Any other answer? So that was the correct answer. From Q, Singleton said Q, on occurrence of a B, you will either stay in Q using this transition, or you will take this transition and go to P. So the possibilities are P and Q. So here I will go to PQ. which means I go to this state S3. So from set of states Q, on occurrence of an A, I will go to empty state, which I will draw in blue if you like, so as not to clutter this diagram. This is also on an A, and on a B I will go to PQ. Agreed? This is the kind of two transitions I got from that. Now, of course, I have one state called PQ. From PQ on an A, where all can I go? So I have to take where all I can go from P and union it with where all I can go from Q on an A, right? So can somebody tell me what is? I will remove this. And
Both
now what?
The P.
Okay, very good. So what we are trying to calculate is delta hat of PQ in NFA. Huh? So this is in NFA N. PQ on letter A. That will take you to P on an A will take you to either P or Q, right?
Yes.
And Q on an A will take you to empty set. So union of this will give you back PQ, right? Agreed?
Right. Agree.
Yes.
So you will get a self loop on an A here. That is from set of states PQ on an A, you will stay in PQ, right? And on so PQ on an A, you will stay in PQ, and on a B, what will happen?
Same PQ.
P comma Q.
Same PQ. Very good. I am not able to hear you. Can you say again loudly? Hello? There was a question. So is this clear to you?
Yes, sir.
Now from phi on an A, where can you get? Of course, by definition, you know, we have to take every state in phi and take the delta trans, but there is no state in phi. So the union will give you empty set. So always phi will always return phi on any letter. That is by definition of delta hat. Okay. So this line will always remain same for all possible NFAs. Okay. Recall this definition of delta hat. Delta hat A on an X. This is very important definition. This one. Delta hat of A on an A is actually this. Union of all states in Q, delta of this. If A is empty, then it is an empty union which will give you empty set. Okay. So that's why phi will give you empty set. And so what we are saying is phi on either A or B will remain in itself. Okay. And what is my set of initial states? It was singleton P. So this is my start state. So I have defined this automaton here, you know, by using this. I have not defined what are the set of final states, but I have defined this automaton. Is the construction of the automaton graph clear to you? Any questions here? Just how to construct. I was told that this is one of the slightly more intricate advanced part of this course. So if you are getting this, very good. And I think you are getting it. Okay. So that what we constructed here is given in this one line. That is for the set called capital A in my DFA on a letter A. Where do I go? I go to a set which is called this. And this set is actually delta hat in the NFA from the set of states A on letter A. That is what we did. So we populate this one line tells you how to populate all these entries in this table. Okay. That is what we did. Now, if there is no question here, let me come to the last part of this DFA construction. What is going to be the set of final states in my DFA, right? Now we already saw that if you start with the set of initial states of NFA, which is this capital with curly bracket P here, you know, and if you wind up in a set after a string which has a final state in it, then the string will be accepted. Remember this property. This property. If I start with the set of initial states of the NFA, and after if I calculate delta hat and I wind up in a set of states which has a final state in it, which is same as intersection of this and f is non-empty, then I should accept the word, and if that is not the case, I should reject the word, right? This is the defining property of NFA accepting a word. So basically in this DFA construction, all the sets, which have a final state in it, final state of NFA in it, should be marked as a final state, right? Is the reasoning clear to you? So all the states, there are four states in DFA. They are each set. Each of these sets which has a final state of my NFA in it will be called a final state of the DFA. So final state of DFA will be marked by a, I don't have a space here. I should put an F next to it, but I will put an F here. So is this a final state of the DFA? Curly bracket P? Yes, because curly bracket P. Hello? Yes? Somebody saying something, but I'm not able to hear. Okay, so is this a final state of my DFA? This set intersection, what is my set of final states here in NFA? It is just curly bracket P. Here I am considering this candidate state curly bracket P. So I take curly bracket P intersection curly bracket P, which is non-empty, right? And hence I will mark this as a final state. That is, I will double circle this, right? What about Q? Curly bracket Q intersection curly bracket P is empty. So there is no final state of NFA inside this curly bracket Q. And so this I cannot mark as a final state. So this will remain a single circle. What about PQ? PQ intersection set of final states contains P, right? This contains a final state of NFA called P. So this also is a final state. So I have to mark this as F. That is, I will double circle this also, right? And this gives me the final set of final states of my DFA. So there are four things I did. So how I mark the set of final states is clear to you. I take each of these sets and check if which of these have at least one final state in them. If they have, I mark this as a final state of my DFA. If they don't have, I don't mark it as a final state. Is this clear to you?
Yes, sir.
Okay, so there are four things we did in this construction. Given this NFA, we first consider the set of its states and take all possible subsets of this Qn of NFA. In this case, we get four possible subsets. So each of these becomes a state of my DFA, right? Here, these four states that I have drawn. One is called phi, one is called P, one is called Q, and one is called PQ, right? Now, on each letter from each of this this state in DFA, which state should I go? Equivalently, from this set of states of NFA, on a letter A, where should I go? That is given by delta hat of that set on that letter by this definition. So you see, on the left hand side, on the right hand side is the NFA expression, on the left hand side is the DFA expression. And we say delta of M on a state called capital A on A in DFA goes to a state whose name is given by this set. Okay, so we mark the entries of this table. Then what was the initial state of my automaton? Same as the set of start states of my NFA, right? I determined the set of initials, the initial state of my DFA. And then finally, I went along, I examined this list of states and checked which of these sets had at least one final state in them. If it has, I mark it as a final state. Otherwise, I don't mark it as a final state. And that completes the construction of this DFA. Okay. And then the claim of Rabin and Scott was that this DFA that you constructed will accept exact without, and this has no guesses in it. Remember, there is exactly one transition from each state of this DFA to another state. Agreed? So this is an automaton without guessing, and it will recognize same language as the original automaton. And we will see a proof of this, although it should be clear to you from this proposition. This thing should convince you that what we have constructed is an automaton which will recognize same language as the NFA. What we have done is this calculation of delta hat on a word that we did is what this DFA will do. Okay, we'll see the proof, but first learn just the construction. If you are able to construct the automaton, that is half the battle. So any questions here? Because we are going to consider one more example. I think people are very shy about asking doubts. Remember, there is no stupid question. There can be stupid answers.
Sir, I have a slight confusion with that A proper subset of Qn when we are trying to find the final states for M.
Okay, so you see, we have got 4 states in my DFA, right? That you agree?
Yes, so these 4 states are of Qn.
These are 4 states of Qm, right? These are DFA states. NFA states are just P and Q. There are 2 states in NFA.
But I mean, for the language, shouldn't we just start with the start states of N? And here the start state is only P.
So we are starting with the set of start states of N, no? Okay. What I will do is I will give you another example, and that will make this clear. Okay. We are not going to calculate the transition function, but we are going to calculate the rest. So let me add a page. I think it's good that you are asking this question here. So what I'm going to do is I'm going to draw this automaton again. I have got, self loop on an A, and on an A I go here. On B I don't do anything. Here I have a self loop on a B, and I also go here on a B. Right? This was our automaton. Right? Do you agree? With 2 states, yes. One is called P and one is called Q. Right? And this P was the initial state, and this P was also the final state, right? Now I'm going to change this automaton. Okay, I'm going to have 2 start states, P or Q, which means what? The automaton, and I will have only one. Oh, I'm sorry, that messes up the diagram. So I'll have this single state Q, and the arrow will go there. Oh my God. Okay, let me draw this again. Give me a minute to complete the diagram. Okay, mess data. So is this automaton clear to you? Only thing I'm saying is here I have non-deterministic start state. That is, I can either start in P or Q. Okay. So is this NFA clear to you? We just have an NFA. There is no DFA yet.
Yes, this is clear.
What is the set of states of this thing? That is Qn. PQ.
For this, it's right? P and Q.
Right. What is the set of start states of this Sn? It is also a set. It is PQ. Which means what? This automaton can non-deterministically start in P or it can start in Q. And there will be an inspired guess which will tell you whether to start in P or in Q. We saw an example of this. Is this point clear to you?
This is clear.
Okay. Now, when I construct the corresponding DFA, what is going to be my set of states of this automaton? I'll have either an empty set, or I will have P, or I will have Q, or I will have PQ. Right? These are all the subsets of Qn. So I will have 4 states in my DFA.
Clear. As in all these, the transitions were clear. My question was about
the start state.
No, the final state calculation.
Okay, but start state is clear to you. This is my start state of DFA. Right. Now, what was my set of final states here? P, right? So my Fn was just P here, right? In NFA.
Yes.
What I do is I take intersection of Fn with each of these.
Yes, so why do you take an intersection with each of those when we only need to check it with the start states? Like, shouldn't it be?
No. This we are checking whether if we wind up in one of these states, if this is the last state of the DFA, see, on a run, you will wind up in some state of DFA. That means you will wind up in one of these 4. Do you agree? When we run this DFA on a...
My question was answered. Yes, I understand.
Right. Excellent. So that is why we take intersection of each of these states with the set of final. We check basically if a final state is in one of these. And if we wind up at the end of the DFA run in one of those states which has a final state in it, in NFA with guesses you would have had a run which would take you to one of the final states, right? So your question is answered. So this will be my, I will draw it in blue. This will be my possible final state and this will be my possible final state, right?
Yes.
And then on A and B, I would draw the transitions, which we did as before, right? Okay, excellent. I'm glad that this question was asked. And then you can, from this theorem, you can. Yes, please. I am not able to hear you. Can you repeat the question, please? If you have a bad internet connection, please ask on the chat. I'm sorry, somebody had a question or was unmuted unnecessarily. One of the two. Okay. One more example. Suppose we have this automaton. What is going to be my set of this is my Qn. My set of start state just contains a single P. My set of final states Fn is also single R, right? And then the transition function is drawn here, so I will not write it. This is my NFA. N. So in my DFA, okay, there's one more thing. Before I do this one, I want to go back to the previous example. So here was our DFA that we calculated, right? Now, one thing to notice here is if you start with this start state, you can possibly go to phi or you can possibly go to this set called PQ. But there is nothing entering this set curly bracket Q. So this is an unreachable state in my automaton. I can never reach this state. If I start with this state, no matter what string I have, I will only be able to reach, states which can be. You can see that this curly bracket Q is not reachable from P. There is nothing coming into Q. So how will I ever enter this state Q in the automaton? So I have this unreachable state. Do you agree? Well, state Q, right? And so this calculation that I do from Q where I go is sort of not interesting because I will never enter Q. Why do I bother where I will go from Q? Because I will never enter Q during any run of my automaton on any word. So this Q is redundant and can be removed. Do you see that? I will give you another example of a DFA page. Suppose I have a DFA which on an A goes here. On a B it goes here. It doesn't matter what we have. Then on both AB it remains here. This on both AB it remains here. And then there is another state which on an A or a B goes here, and this is the final state. But you see, the point is, if I start here, whatever word I consume, I will stay only within this part of the automaton because there is no way to enter this state. So this is an unreachable state. Although it is part of our set of states, it is not serving any function. We can remove it from the automaton together with all the transitions that go out of it. And I will not change the automaton, right? Any confusion there? So here is an automata with some unreachable states. And those unreachable states are redundant. They can be removed from the automaton. And you will get a smaller automaton which will do the same function. Yeah? This is true of any DFA. Given any DFA like this, you can always add some stupid states which you will never go to. And then, what you do from that state doesn't matter because you will never reach them, right? So there can be stupid DFAs with unreachable states. Unfortunately, this subset construction gives rise to such unreachable states. Okay. So although we have 4 states here, one of the states Q was unreachable here, and somehow the construction required us to calculate, transitions from unreachable states also. This is one thing I wanted to point out. Okay. Now, here I have another automaton, DFA. We are going to do the subset construction for this one. Okay. So my Qn is this set of states PQR. My set of start state is curly bracket P. My set of final states is curly bracket R. I mean, I could have had more than one here, but somehow this is from Cozen. This is what he has in this DFA. So what is going to be the set of states of the DFA? Anybody can answer? It will be what is drawn here, right? Empty set, just curly bracket P, curly bracket Q, curly bracket R, curly bracket PQ, curly bracket PR, QR. Take all possible subsets of PQR and you get the set of states of this DFA, right? Agreed? Any confusion so far? Okay. What was my set of start states of this NFA? Capital SN was just curly bracket P, right? And so this curly bracket P becomes my start state in the DFA, right? So far so good. What was my set of final states in my NFA? It was curly bracket R. So I examine each of these sets, and anything which has non-empty intersection with Fn, that is which contains this set R, will be marked as a final state. So this will be a possible final state. 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 By the condition that this set, the set that you are considering, intersection Fn is non-empty. That is, it has one of the final states in Fn in it. So is the marking of, forget the transition function, is the marking of the set of states, the initial state and the set of final states of DFA clear to you? I think this should be very clear.
Yes, sir.
Agreed? And now for each of these sets, such as PQ, we have to calculate delta hat of, so suppose you are trying to calculate the entries within this row marked PQ. So what you will do is you will take delta hat of PQ on letter 0 and fill in that entry here. It turns out to be PR, and you will calculate delta hat of PQ on 1, and that entry will come here. This entry will come here, right, on the column 0 and 1. That is what you will calculate. But before doing that, there are going to be a lot of redundant states here, unreachable states here. So there's a trick that you can use, and I'm going to calculate this automaton with that trick. So what I'm going to do is, instead of writing down the set of all possible states, I will first write down the start state, which is Sn, right? So I'll have curly bracket P is definitely one of the states of my automaton, and I'll mark this as the start state. Now I've got two letters 0 and 1, right? So from this set, I will calculate on 0 where all I can go. So can somebody tell me what is the set of states I can reach from curly bracket P on a 0 in this NFA? Hello? What will be the entry here? It is same as delta hat of curly bracket P on a letter 0. Yeah. So what do I get? See, from
PQ. Set PQ.
No, I'm going on letter 0, not on 1.
Only P.
Only P. Okay, so that's what I get. And then on a 1, so from set of states P on a 1, I will go to PQ.
PQ.
Was there a question here? P on a, this is what we did. We calculated this as PQ and then filled in that entry here. So this entry came here, the first row came here, right? This is what we did. So now I know that in my automaton, from curly bracket P, I can go to curly bracket P, or I can go to curly bracket PQ. So next I will expand the curly bracket PQ, right? because this is a reachable state, because this is an initial state. From that I can go to curly bracket P or curly bracket Q. So I will expand this. Now what, from PQ on a 0, where all can I go? PR. Are you able to see this? Because from P on a 0 I can stay in P, and from a Q on a 0 I can go to R. So together from PQ on a 0 I can go to P or R, right? So I filled in this entry. From PQ on a 1, where all can I go? I can go to PQR, right? So I have two new entries called curly bracket PR and PQR. So I'll add rows corresponding to them. So I will add a row for PR and a row for PQR, right? And now I have to fill in the table for them. So I'm only generating the subsets which arise in this table. Those which don't arise, I'm not going to expand. I mean, I could have done the full table like this, but instead I'm going to economically only expand this. So from PR on a 0, where else can I go? Anybody can answer?
Only P.
Only
Only
P.
P.
Right, because R on a 0 will die. You can't go empty set. So we take right. See, and PR on a 1.
PQ.
PQ. Now both of these are the states I have already expanded, right? P is expanded in this row, PQ is expanded. So I don't need to add any further row to the table. Now I go to PQR. From PQR on a 0, where will I go?
P and R.
P and R. Now I already got a row for that, right? And then from PQR on a 1,
PQR.
PQR. So you see, now I have already covered all the states which will arise in my automata, and I don't need to expand the remaining rows of this table. So I am only expanding the reachable states, right? This is a trick that you play. So you will get a shorter table. Got it? This is a slight optimization on that construction, there. You know, where first I listed all possible states, you know, and then I expanded each one out. Instead, I do it on need to, you know, on the need basis. That is, I first start with the initial state of my DFA and see which all states it leads to. And for those states, I expand them, and then I keep doing it till this table becomes closed. So is this trick also clear to you? Okay. Now,
Yes,
what
sir.
is my set of final states from these four sets? Will this be a final state? Curly bracket P, is it a final state?
The last two will be final.
Yeah, so curly bracket P is not a final state because intersection of curly bracket P with this curly
It's
bracket
fine.
R is empty. Similarly, PQ is not a final state. Last two will be the final states, as somebody said. Very good. So now you know how to construct this automaton fully, and we can even draw this automaton just for convenience. I think there may be a figure already on the following slide. So this calculation is given in Cozen. This is exactly what we calculated, right? This is what we calculated, but I don't know if there is a figure for this. So let's draw the figure for this. So I will have one state called curly bracket P. I'm omitting the curly brackets, right? Then I will have a state with curly bracket PQ. I'm omitting the curly brackets here. Then I have a state called PR. And then I have a state called PQR, right? These are the four states of my DFA, right? Do you agree? Now these two are the final states. We marked it here with capital F. So these two are my final states. My initial state is this. Agreed? So is the construction of automaton there? We have to write the transitions, but this is the automaton that we constructed. Now from P on a 0, you will stay in 0. So I will draw these transitions in red, and then I will mark this as 0. From P, curly bracket P on a 1, I will go to curly bracket PQ. So this is my transition on 1. That is this entry. Now PQ on a 0, I will go to PR. So I will go on 0 to PR, and on a 1, I will go to PQR. So this is my transition on a 1. Similarly, from PR on a 0, I will go to P. And from PR on a 1, I will go to PQ. So 1 will return you there. And from PQR on a 0, I will go to PR. And on a 1, I will self loop. This is the automaton that I built. Now, remember, this NFA was recognizing all strings where the second last bit was a 1, right? It was magically checking when it got a 1 whether it was a second last bit or not. It has not yet seen the rest of the string. And if it was 1, it would move to Q. And then it would consume one more bit and then accept. But if any more letters came after that, it would not accept, right? Now look at this automaton. So let's consider a string 0, 1, 0, 1, 1, right? What will this NFA do? On this 0, it will, okay, so I think it is interesting to see the run of, compare the run of these two automata on the word 0, 1, 0. What is my, I'm running out of space, but let's do it in black here so that you can. So my string is 0, 1, 1, 0. Let's take this simple string. So what will be the run of NFA? I will start in
Sir, you are not audible.
Sir, you are muted.
now. Is it okay?
Sir, it's okay now.
Yeah,
Yes,
I don't know how MS Team
When-
does this.
When you start this script,
Example
then
again.
Yeah.
Yes. So we have this.
Yeah.
We have this NFA, and let's consider how it recognizes string 1, 1, 0, 1, 1, 0. First, you agree that this is a string which is accepted by the NFA because the second last bit is a 1, right? And the way it will work is it will first be in the state P, then on consuming 0, it will stay in P. Now it gets a 1. It has a choice of either staying in P or going to Q. But it will magically guess that this one is not the second last bit and it will choose to stay in P. This is the magical choice. Then it gets a second one. This time it guesses that this is the second last bit and so it will move to Q with an inspired guess. And then it will get a 0, so it will move to R and accept. This is the accepting run of NFA. Agreed? Any confusion? Hello? I hope I am audible and you are able to get the run of the NFA.
Yes, sir.
Okay,
Yes, sir.
now I'm going to do a run of the DFA that we constructed on this word. So what will happen? I'll first be in the set curly bracket P. From curly bracket P on a 0, I will stay in curly bracket P. Agreed? This is that self loop. Then on a 1, I will go to curly bracket PQ. Agreed? Because I have only one choice in DFA. So on a 1, I will go to PQ. What it says is that on the string 0, 1, which I have consumed so far, my set of possible states I can reach is PQ. That is what it is remembering. That's why it's going to this set PQ, which is a state of the DFA. From this state PQ, on a 1, where will I go? I will go to PQR. Right? And then on the next 0, I will go to state PR. So this is my run of the DFA on the same word. And this final state has got an R in it, which means there exists an initial state from which there is an accepting run in the NFA. That is why this run is accepted by the DFA. So what DFA tells you is all the states that you can reach in the NFA, you know, from the set of start states. And since that has a final state in it, you will accept. So I hope the working of the DFA and the NFA are clear to you from these two runs that I have drawn. Okay. I think this is the key point. And I think you should study this example very carefully to understand the difference between how NFA run happens and how the corresponding DFA run happens. So I'm going to pause for a minute and let you look at these two runs. On the top in red is the NFA run. On the bottom with curly brackets is the DFA run, where each state of DFA is a set, right? So this is what we have. So from this, you can see that NFA will accept if the second last bit is 1, DFA will also accept if the second last bit is 1. You know, somehow that guessing it has absorbed by maintaining sets of states which are reachable. Okay, I know this is involved. That is why this work led to winning of a Turing Award. But I'm sure with some amount of study, you will all be able to understand this. This is an advanced part of the course, but I'm sure you are up to it. At least the construction you should be able to make. And you should also be able to intuitively see that this DFA does the same job as the NFA, but without using any guessing. Okay, I will assume that you have understood this. And then what we will do is actually this is the construction. Formally, it is written like this. So the set of states of my DFA is the set of all subsets of Qn. That is, whatever were the set of states in Qn, you take any possible subset, I will get a state of Qm. This will have inaccessible states, okay, unreachable states. But this is technically the set of states. Then we calculated, you know, from a state marked as capital A in DFA on A, where do you get? In an NFA from that set of states A, on an A where all you can reach. So this was our delta hat. Our start states was this, and this was our set of final states. So I think this 4 lines is exactly what you used when you constructed those tables yourself, right? When you constructed these tables, you basically use this 4 lines, and this is the formal treatment of that construction. Now, what Rabin and Scott said was not only they gave this construction, but they also proved that the language of this constructed M is same as the language of N. That is, any word which is accepted by DFA, a word is accepted by this DFA if and only it is accepted by the NFA. And for that they give a proof. So this proof is the advanced part of this course, but with some study you can understand it. So this is what Cozen calls, first they prove a lemma, and in Cozen book this is called lemma number 6.1. And what it says is, for the we have now 2 automata. Remember, NFA N and DFA M, right? From N we have constructed the DFA M, right? And what it is going to do is it is going to relate the extended transition function of M to the extended transition function of N. And this is the key property. Okay, and this property holds for any subset of Qn and for any string, right? So basically for any A and for any X, this property should hold. This is what Cozen proves. Now this is very easy to see, because how did we construct this delta M? Anybody remember what is delta M of A on a letter A? Do you remember how we constructed this? This was just the delta hat in N of A on a A. This was the definition of delta A. See this. This was the definition of delta M on AA. Right? This is how we constructed the table. For any set, any state of DFA marked capital A, this is how we constructed the state to which it will go. So this property is certainly true when X is a single letter, because that is how we constructed it. For epsilon, both sides will be. So now, because this is true for a single letter, by induction we can show that it will hold not only for a single letter, but for any string X. Okay, that is what we prove. And the proof is by induction. So first we prove this property will hold not only for a single letter, but for any string X. And to prove that inductively, first we have to, we use structural induction on the string X, and we prove it first for the case where X is epsilon. So small delta hat of A epsilon will give you what? By definition, this will give you capital A, because delta hat of anything on epsilon is equal to A. This is the property of the delta hat, that on epsilon it does not change the state. You remain in the same state, on consuming string epsilon. Similarly, capital delta hat on A in NFA will also give you A, right? This you can check the properties of capital delta hat that we had constructed. Will also give you A. If for any NFA this is true, for any DFA this is true, and so both LHS is equal to RHS. So do you understand that this property holds for epsilon trivially by definition of this small delta hat and definition of capital delta hat? So here is the justification, and this theorem is true for empty string. We have to prove it for all possible strings. Okay. I hope this basis step is clear to you. Any difficulty?
Yes, sir. It's clear.
Yeah, you can study it and ask it. Now we have to prove this property for longer string. So what we will do is we will assume that the property is already true for some string X. Yeah, so we assume that it is true for X, and then we will prove it for a longer string called XA. Right? This is the induction step. So we'll assume that the property holds for X, and we'll prove it for XA. And the proof that it holds for XA is given here, this part. This is the assumption. So we start with the left hand side of our property, where we want to prove it not for X but for longer string XA. So we start with small delta hat of A on XA. Right? Now this is equal to what? If you go and check the definition of a small delta hat for DFA, this is same as delta of delta hat on the simpler string X, followed by transition on. So first you run the automaton from the state called A on the string X, and whatever state you wind up with, you take one more transition on A. This was the definition of delta M. You should be able to check the definition of small delta hat given earlier and understand this step. This is nothing but the definition applied. Okay. Now for this part, which I have overlined in red, by induction hypothesis, we can write this down as this part. Okay. Let me rub that because you are not able to see that cap. You will write it down as, let me highlight it, because then things become easier. So that red underlined part you can write down as this. Why? Because induction hypothesis. We have already assumed that this red overlined part is same as this yellow highlighted part. That is the induction hypothesis. Okay. And then by definition of delta M, this is same as, how did we define this transition delta M of the constructed DFA from NFA? This way. This is the definition of delta M. This one. This part. Right? Delta M of A on anything is same as this. So we just apply that definition and we get this line. Okay, so you will have to try and do this proof a little bit by yourself, but it's an easy thing. And then this is same as this. This we had already done. Sorry, this is not lemma 6.1. This is 6.2 or maybe even 3 or 4. I don't remember the number. Okay, so this is some lemma 6 point something. Okay. Okay, so this is a simple 4-line proof that these two are the same. That is, what is this? I will assume that you have understood that this lemma holds. What it says is, starting from any state called capital A of the DFA, on string X, you reach some state in DFA That is same as starting with set of states capital A in NFA and reaching some set of states. And these two are the same. Okay.
Sir.
Given that.
Hello, sir.
Yes.
Is there any difference between delta and delta cap?
Yes. Delta is defined only for a single letter. Delta, let's talk about small delta. Small delta will be defined from a state of the DFA on a letter. It will give you an element of set of states. Let's say it will go to some R, right? Whereas delta hat will start from a state and take any possible string, including epsilon or AA or AB, and give you a state. Okay. So the difference is delta and delta hat will agree on a single letter, but delta hat is defined on many other strings, not just a single letter A. It is also defined on epsilon, it's defined on AA, it is defined on ABA, right? That is the difference between delta and delta hat. These are different functions. So yes, you are dealing with many different functions here in this definition. And in fact, delta hat is defined using delta. That is why you were asked to revise the definitions of small delta and capital delta in the last quiz before coming to this class. Okay, so I agree, there is notationally there are many things. There is small delta, there is small delta hat, there is capital delta, and there is capital delta hat, right? And you are using all four in this proof. That is what makes this proof advanced. But if you study this, things will become clear to you. So I will leave you to study this because proofs have to be read by yourself. Let's assume that this theorem is true. That is, from a state called A in DFA, which is actually a set in NFA, on a string X, if you go to a state called B. So what is this saying? If in my DFA, starting from a state called X on this, if I go to a state called B, now remember these are states in DFA, but these are sets in NFA. Then in NFA, if I start with a set of states A on X, I will go to the set of states B in NFA. That is what it is. This is in NFA N and this is in DFA M, right? This is what this theorem is saying. Okay, with that, we can actually show that the language accepted by DFA is same as language accepted by NFA. When is a word accepted by DFA M? Whenever small delta hat of the start state of M on some string X belongs to its final state. This is the definition of acceptance for a DFA. This is DFA acceptance in terms of delta hat. This is same by construction. This is same as this. Small delta hat is same as capital delta hat of Sn on X. This is by our previous lemma. And the accepting states of my DFA are defined as this. So this is the acceptance. This is combining two steps. One is the previous lemma and the acceptance condition for the DFA constructed. And then this is it. So this is a simple 3-line proof. I would urge all of you to try to understand this proof offline. And if you get confused, you can ask one of the TAs or you can ask me as doubt, and I'll be happy to individually guide you through this proof. But this is the best I can do at the moment. We are nearing the class. So what we have done is we have proved in these 2 slides, we have given the 3 slides. We have given the proof that this construct by subset construction, if we construct a DFA from an NFA, it will recognize the same language. So there are 2 parts to this lecture. One is the DFA construction, which all of you should be able to do. And then there is the proof that it is actually recognizing the same language as the original NFA. Till you are able to construct the DFA from the NFA and intuitively understand that it will recognize same language, you have done half of the job. And many questions, you will be asked many questions where you will be given NFA and you will be asked to construct the corresponding DFA. Okay. And then the proof part is the advanced part of the course. Only some advanced questions will be asked from that. Basically, you should understand the construction and intuitively understand that it does the job required to give this result. And then if you are I'm sure many of you are curious why this works. So that is why the formal proof is given. And for giving that proof, Scott and Rabin, got their Turing Award. So this is Turing Award winning work that you have understood. Okay. One last thing. Okay, if you are given an NFA n with, let's say, small n number of states, right? So here we are given an NFA with 3 states, right? What is the number of states of my DFA? Technically, we are considering every subset of, where is the construction? Yeah, technically every subset of Qn is considered a state of my deterministic automaton, right? So if my NFA has got 3 states, my DFA will get how many states? If my NFA has got 3 states, my DFA will get
8 states.
8
yeah,
states.
why? Every
2
subset.
raised to 3.
Every substep.
Yeah, so 2 raised to n, right?
N.
Right. So technically I get 2 raised to n states in my DFA. Some of them are inaccessible and I may get lucky and many of them die. So instead of 8, I am left with only 4 states, right? Agreed?
Agree.
So sometimes I may get less than 8 states. But in the worst case, I know that I will not get more than 2 raised to n states. That you are clear by the construction. So given an NFA with n states, my DFA M, DFA M will have less than 2 raised to n states. That is clear, right? So upper bound on number of states in the worst case is 2 raised to n. That is exponentially large. So if I start with an NFA with 20 states, I will get a DFA potentially with 2 raised to 20 states, right? Which is a very large number. So these DFAs can get very large. Now it is possible that there are 2 ways in which this DFAs that I get can be smaller. Okay, 2 ways. What are those 2 ways? One is that there may be unreachable or inaccessible states, right? Right? Like in the example we saw that only 4 out of those 8 states were reachable, right? And second is that you can construct a stupid DFA. So I'll give you an example. Consider this DFA, with 2 states, P and Q, which I will write in black, P and Q, and a single letter alphabet A. This will recognize all strings of A with even number of A's. Is that easy to see? Do you agree? Who doesn't agree? This recognizes, even number of A's. But I can draw a more complicated DFA with 4 states, here. And then on every A, I will move this way, this way, this way, and this way. And then I will call this as my final state and this also as my final state. This automaton has got 4 states, but it is also recognizing, all words with even number of A's. So there can be wasteful automata which are using more states. These 2 automata recognize the same language, but this has more states than that. So maybe the DFA that we constructed in the subset construction is stupid and it is using more states than required, right? So there may be potential for improvement in the subset construction. So the big question that you ask is there a better construction which is guaranteed to give the smaller size DFA in the worst case? That is, for any NFA, it will consume less than 2 raised to n states. For some, it will definitely consume less than 2 raised to n states, as we saw. But is it possible that there is a better construction than subset construction, which will consume less than 2 raised to n states? And that's a big question. We'll deal with that in the next class. Okay, and that will motivate several other lectures that are coming. But this is what we did in subset construction. So I hope you will study this And then in the next class, we will deal with what is called automata with silent transitions, what I call radioactive automata. Okay, so there's some fun coming in the next class. And then this radioactive automata will recognize, things like set of decimal numbers as strings, So 3.12 or 0.2 or even just 0.2, it will recognize all such strings, but it will not recognize, strings like 3.12.3, with 2 decimal numbers. So the easiest way of recognizing such decimal number strings will be by constructing this radioactive automata that we will consider in the next class. And those are the most powerful finite state automata we will consider. Okay, so with that, I would like to close today's class. Any questions?
Sir, can you also upload the slides?
I will do it in half an hour. The recording will take little time, but you can find the recording on the team itself, right?
Yes, sir.
I will do that in half an hour. And please study these slides before coming for the next class, because otherwise there is a continuity and you won't get it. Thank you.
Thank you, sir.
Thank you.